Hello everybody, if you can hear, just put OK on the chat. Is it loud and clear? Hello everybody, is it loud and clear? If you can hear me clearly, you can put a thumbs up or OK on the chat. Hello everybody, can you hear me clearly? Okay. Good evening everybody. Welcome to another edition of Helpline. We'll be discussing questions that you find difficult so that you can attempt it much more in a much more clear way. Today also we'll discuss some questions that some of you all have requested. We'll take fluid dynamics. Fluid dynamics. Now, this is an A-level question, examination question. So, it will be helpful when you try to analyze this particular question. Right. Some of you are still joining in. We'll start in exactly 2 minutes. Some of you are still joining in. In 2 minutes, we'll start. constant along a streamline. Constant along a streamline. So here you go. P plus half rho V squared plus rho GH. Constant along a streamline. 2009 A-level question. Identify each term. Like I said earlier also, you can separately identify each term. P you can say pressure. Rho you can say density of the fluid. V you can say velocity of the fluid. G you can say acceleration due to gravity. H is height from datum. Or you can clearly put the initial term. P is work done by pressure per unit volume. Half rho V square. Kinetic energy per volume. Rho Gh, potential energy or gravitational potential energy per volume. Okay. These are nicely taught in your theory. You can either substitute any one of them in the relationship. Right. What are they telling you? An ancient waterway which supplies water to a pond consists of 3 stages as shown in the figure. The 3 stages are there. They are shown in the figure. Stage 1 is a rectangular horizontal open water. Rectangular horizontal open water channel. So they have drawn it like this and given. Then you have stage 2 that's planted. And stage 3, of course, like this. Stage 3. So here you go. To consider from here. This part is a reservoir. That part is a reservoir. So from here, water is traveling through. Here, water is traveling through a rectangular horizontal open water channel originating from a rectangular outlet of a large reservoir. So rectangular outlet of a large reservoir. The water streamlines will come this way. Water is coming that way, this way, and then what? Moving out. This is what's happening. Water is moving out. Right, no? Okay. Right. So what's happening here is liquid is traveling downward. Liquid is traveling and then moving out. So you need to understand exactly what they're asking you. Here they have drawn it for you all. There you go. It's 3D verse. 3D verse. Right. Right. Another rectangular open water channel having same flow width as stage 1 but runs as a slope is shown in the figure. Width of the channel flow is 0.5. So this width here 0.5 meter. This here 0.5 meter. There you go. Width is particularly marked. Right? What else? Stage 3. Stage 3 is linked to stage number 2. Horizontal shallow channel of rectangular cross section with much more broader width. Now here the width is 10 meters. Huh? Broader width 10 meters. Broader width 10 meters. Water coming from the second stage enters the channel and starts flowing orthogonally. Orthogonally means outward, perpendicularly, creating a waterfall. So there's a waterfall situation. So what's happening is water coming out from the channel travels through this, comes out, falls as a waterfall. It's like a garden waterfall. Yes, it's like a garden waterfall. Right. So complete the diagram the way they have given here. There you go. This particular part. There you go. Right. So if I draw the 3D version, water is flowing out and coming outside. Water is flowing out. Water is coming from the reservoir here and then coming outside. Okay. So P stands for pressure. Half rho V stands for kinetic energy per volume. Rho GH is gravitational potential energy per volume. Is constant along a stream line. That's the theory. Right. Let's start working. Part A. Part A. Have a look. At steady state, waterfall carries 1.5 cubic meters of water per second. So all of you all know 1.5 cubic meters per second is coming out. Throughout this, the volume flow rate is always constant. Volume flow rate coming out from the reservoir. Volume flow rate traveling through the tube. Volume flow rate going through stage number 2. Volume flow rate coming out of stage number 3. All are what? Same. Volume flow rate throughout is the same. Now, these are we learn in equation of continuity. A1 V1 equals A2 V2. That means throughout the volume remains always what? Constant. Throughout the volume always remains constant. Right. If you look at this carefully, if the speed of water flowing at the exit of stage number 2 is 10, now read, if the speed of water flowing at the exit of X coming here, I mark with red, exiting velocity is given. Exiting velocity is given 10 meter per second. Question they are asking you is, calculate the height of water level from channel at X. Height of water level of the channel X. That means they are asking you to find its height. How high is the water? Okay. So if you view this three-dimensionally, water is coming out. Water is coming out with a velocity 10 meter per second. Water is coming out with a velocity 10 meter per second, which is equal to 0.5 meter. They are asking the height. Part A. So all of you all know the theory. Volume flow rate is area into velocity. Volume flow rate is area into velocity. What is volume flow rate? Volume flow rate here is given 1.5 cubic meters per second. 1.5 cubic meters per second. What will be your area? Area is 0.5 into h. 0.5 into h, velocity is 10. 0.5 into h, velocity is 10. Simplify this, 1.5 equals 5 times h. From this you can build the relationship h is equal to 0.3 meter height. That means everywhere in stage number 2, don't forget that. Everywhere in stage number 2. Stage 2. The height here is going to be 0.3 meters. 0.3 meters. Right. Part B. Part B. Look carefully. Part B. Assume that the height of water level in the shallow channel stage 3 height is equal to the height of water in stage number 2. So this height and this shallow channel, both heights are same. Calculate the speed with which water flows out from the shallow channel. Now they're asking here what will be the velocity. So here also, I think now we can easily solve this. Now the width is going to be so much. Width is going to be 10 meters. Water is coming out this way. Water is coming out that way. Height of water is same. Height of water is same. Height of water is same, 0.3 meters. Water is coming out with a velocity we don't know. We have to find it. So by drawing it like this, now you have idea. Water is coming out in a particular slab form. So volume flow rate A times V, 1.5 cubic meters per second. Area is 10 into 3. Velocity is going to be V2. From this V2 velocity, you can find stage 3 velocity, 0.5 meters per second. 0.5 meters per second. I think that's what they want. Calculate the velocity in the shallow part. 10 meter width, same height as the stage number 2. So volume flow rate you can easily find. Volume flow rate is same. Area we can find. Velocity we can find. Okay, that's a simple work. Actually now from the beginning, what are we doing? We are just using equation of continuity. Volume flow rate. Volume flow rate here, volume flow rate there, and volume flow rate here. All are what? Same. So the volume flow rate throughout the motion does not change. Yeah. Throughout the motion does not change. That is guaranteed won't change. Okay. The rule. Law of conservation of mass. If the density is the same, mass flow rate in equal, mass flow rate out. Densities are equal. So volume flow rate in equal, volume flow rate out. Part A done, part B done. Part C. If the speed of water flow in the horizontal channel in stage 1 is 5. Now horizontal channel, stage number 1. Part C. Part C, I'll do it here. In the same space, we'll try to do it. So here, there you go. Here they are given you the width. Width is 0.5 meters. Height, of course, we don't know. I think we have to find the height. Velocity, 5 meters per second. Water coming out everywhere, 5 meters per second. What are they asking you? Calculate the height of water here. It's there. So here you can say again volume flow rate. Volume flow rate. Area into velocity, 1.5 cubic meters per second. Area is equal to x dash into 0.5 into velocity 5. H dash equals 1.5 divided by 2.5. 3 divided by 5, 0.6 meters. There you go. 3 divided by 5, 0.6 meters. So you can see clearly, part A, part B, part C, we are using only what? Volume flow rate. Still nothing else. Only volume flow rate. So you can see majority of the calculation here is based on the concept of volume flow rate, the width and the height, and sometimes the velocity. We found using what? Volume flow rate. Because volume flow rate here, volume flow rate there, and volume flow rate here, all are what? All the volume flow rates will be the same. All the volume flow rates will be the same. Okay. All the volume flow rates will be the same. Right. So, okay, no. Each part we have found separately whatever we need to find. Now, what are they asking you? Part D. Consider a streamline along the top surface of water flow. Calculate the height y from the channel flow at stage number 2 at x. to the channel flow of stage 1, you may assume that the water leaves to the atmosphere of atmospheric pressure P at the outlet of the reservoir, and water enters shallow channel at X, which is also at pressure P. Right. Look at this carefully. Now you are applying Bernoulli's principle. What are they asking you? Calculate the height y from the channel flow. Y from the channel flow. Look at this very carefully. You redraw this because it's important. Here you go, flat surface. Right. There you go. Right. Look at this carefully. GP equals 0 line. Here they are marked and given y. Here they are marked and given y. All of you all can see water here. Water is traveling at a particular height. Water is traveling here to at a particular height. And then water enters this region with a great width. Water enters this region with a great width. And then water comes in. There you go. What they are telling you here is water is coming out at atmospheric pressure. We know the velocity here. Actually, they have given you the velocity there. Velocity in stage number 1 is 5 meter per second. Velocity in stage number 1 is 5 meter per second. This is the streamline on touch. Streamline on touch. Stage number 2. Stage number 2, what is the velocity? Stage number 2 velocity is 10 meters per second. Stage number 2 velocity is 10 meters per second. What about the height h dash? 0.6. This height here is 0.6. 0.6 meters. What about the height here? Height in the second stage, that is 0.3. Here height is 0.3. Don't forget. Remember here fluid is coming at atmospheric pressure on top surface. Here also it's at atmospheric pressure. Here also it's at atmospheric pressure. Now try to look at this carefully. This water only I marked in blue color. They have told you to consider a streamline exactly at the top. Consider streamline at the top surface. This one in red color is the streamline. It's coming out with pressure P, velocity 5. Here velocity is going to be 10. Now you have calculated this earlier. You have calculated this earlier. You may assume that the water leaves the atmospheric pressure P at the outlet of the reservoir and enters shallow region X also at atmospheric pressure. Calculate this height. Okay, let's apply. Pressure plus half rho W, velocity there is 5 square. What is your height from the datum? From here to here, what's the height? Y plus 0.6, don't forget. Rho W y plus 0.6 g. What about the pressure here, P? Velocity half rho W 10 square. Rho W G, what is the height from the ground level? From this ground level up to here, what's this height? This height here is 0.3. This height here is 0.3. Remember, all heights are measured from where? The datum line. All heights are measured from the datum line. P and P will cancel off. Half rho W. Density of water have they given you? I think all the densities will cancel off. So write the relationship here. Pressure P cancel off. Rho W, rho W, rho W, rho W cancel off. From this you will have y squared plus y plus 0.6 g. Here 10 squared over 2 plus g times 0.3. Simplify this carefully. 25 divided by 2 is 12.5 plus 10y plus 6. 100 divided by 2, 50. Okay, now simplify this carefully. 10y equals 53 minus 6 minus 12.5. 53 minus 6 is 47. 47 minus 10 is 37. Simplify 53, correct, no? 0.3 there. 0.3 there. 0.3 times Pg, so 12.5. There you go, 10.10y. To simplify this, 53 minus 18.5. $34.5. Y is equal to 3.45 meters. There you go. Easily calculating, you can find the height. Y equals 3.45 meters. Check and see whether you got the answer. Check and see if you have got the answer. Okay, no? Carefully, we have applied Bernoulli's principle. By applying Bernoulli's principle, for the top surface, we have easily found y is equal to 3.45. Y equals 3.45 meters. Okay. Right. Next question. Calculate the height of the water level in the reservoir. That has to be maintained for this purpose. Now we can actually build the question from here. Right. What is the height of the liquid? Reservoir is here. Reservoir is here. Vertical height only we are considering it. If you consider streamline like this, if you consider streamline this, you can find the actual height. Actual height is here. From here, if water is coming, there you go like this. Again, apply Bernoulli's theorem. First, draw the picture. Don't be in a hurry. Draw the picture, you can see. To draw the picture, you can easily see. From top of the reservoir here, this is the reservoir. From top of the reservoir, liquid will come and then go down. So if you're applying here, calculate the height h of the water level in the reservoir that has to be maintained for this purpose. So here 3.45 you have found it. If you want, you can apply from here. Remember, here was atmospheric pressure, but water is at rest, right? Area is going to be very, very large. If area is very large, velocity is going to be very, very small or negligible. So here, this is part D. Part E, if you want, separately you can apply. I'll try to apply it here. Part E. So applying Bernoulli's principle from here to here, let's say. Wait a minute. E plus half rho W 0 square, rho W G, y plus 0.6 plus y plus 0.6 plus equal here this side. Pressure P half rho W velocity 5 square plus height is going to be y plus 0.6 rho W G y plus 0.6. Now if you do the calculation here, you can clearly see P and P can cancel off. Rho W y plus 6 y plus 6, this part cancels it. This will cancel off with that. What is remaining is rho W G half rho W 5 square. Rho W cancel off. 25 divided by 2 is 12.5. 12.5 divided by G is going to be 1.25 meters. Height of the reservoir, simple H, even in the picture they are marked and given, that is going to be 1.25 meters. 1.25 meters. Very good. 1.25 meters. Part F. If the water level in the reservoir exceeds a certain value, propose a suitable method to regulate the water flow so the waterfall carries a certain amount of water per second. Use case. I'm sure they have taken you when you are doing your O-level, the Mahavali water scheme, water irrigation system. It's a very important irrigation because it is the biggest and the only first irrigation system in Sri Lanka. In the modern era, early of course the things had much more better. If you look in Polgolla was the first place where they crossed over and they dammed the particular area so that they can turn water towards what? The north. Now in Polgolla, if you have a chance and you come to Kandy for a visit or whatever, always go towards the Polgolla Dam so you can see how the sluice gates work. The sluice gates, they are open down so more water goes out and they are closed. So by moving the sluice gate, you can actually control the water flow. Yes. So a sluice gate will control the volume flow rate. Now those days in the ancient times, this was a bisocopia. We call it a bisocopia. Now, of course, modernly we call this what? Sluice gate. Okay. Modernly we call it the sluice gate. So same system, different name. The same system, different name. So the easiest place where you can see this is when you get a chance to come to Polgolla. Make sure you have a visit there. Polgolla Dam, you can actually see. Actually, you can go close to the dam as well. If you go there, you can actually see how the sluice gates work. There will be certain times, especially during the rain season, that they close and they open, allow water to flow down, because majority of the water is turned towards the north. Okay. Right. So they're asking question number F. If the water level of the reservoir exceeds a certain value, propose a method to regulate the water flow. So we can use a sluice gate to regulate the water flow. You can write there a nice sentence there. By using a sluice gate, we can regulate the water flow. By using a sluice gate, we can regulate the water flow. Okay. Regulate the water flow. Right. Okay, that concludes that question. That concludes that particular question. So hopefully it's good you understood the concept. And always remember, by applying theory correctly, you can always get the answer. Only thing, you must be patient to correctly apply the theory. Right. Look at the next one. Look at the next one. This is 2013 A-level question. 2013 A-level question. 2013 A-level question. Right. Read the question very carefully. Okay. Vertical force lift required for taking off of an airplane is provided by two forces. The vertical lift off force is provided by two forces itself. One arises due to Bernoulli effect, and the other arises due to hitting of air molecules on the wings of the airplane. So molecules will hit on the airplane and rebound, causing a momentum change which causes a force. Right, that's also correct. Orientation and the cross-section view of the airplane when it's traveling along the runway for takeoff is shown in the figure. Right. Here, the bottom surface of the wing makes angle theta in the horizontal direction. So here I'll draw it big. The cross section here. Okay. Bottom surface makes an angle theta. Bottom surface makes an angle theta, right? Look carefully. Okay. Right. A. Take the speed of the airplane in the runway to be in meters per second at a certain instant. And assume that air molecules remain still relative to Earth. So here, mass of air molecule m, velocity is v. Assume it's at rest. Assume the air molecules are at rest. So when the plane is traveling, then by colliding with the plane, the air molecules get a velocity. That's how it's measured. So with respect to the plane means air molecules are getting the velocity of the plane. Right. Consider complete elastic collision of air molecules with the wing. Complete elastic collision. The speed of the air molecules relative to the aeroplane is shown in the figure. Right. It's already given as v. Write an expression for the change in momentum of the air molecule in a direction perpendicular to the bottom surface of the wing. What will happen? It will come here and it will rebound. It will rebound elastically with a velocity. So here only rebounding will take place. We want the momentum change in a direction which is perpendicular. Momentum change perpendicular to the bottom surface. So perpendicular to the bottom surface. There you go. So here theta means guaranteed here theta. So mv cos theta, mv sin theta, mv cos theta, mv sin theta. If I take component, I can just show it here separately on the surface. There will be a component in that direction, mv sin theta, cos sin, and rebounding in the opposite direction, again mv sin theta. There you go. mv cos theta, mv sin theta. Right. What are they asking? Change in momentum in a direction which is perpendicular. So change in momentum, don't forget, final momentum minus initial momentum. Final momentum is in that direction, mv sin theta. Then mark the direction. Minus initial momentum, mv sin theta in that direction. Bring both vectors in the same direction, mv sin theta plus minus mv sin theta in that direction. When you multiply a vector by a negative, direction will change. mv sin theta in that direction plus mv sin theta, there you go. Bring all vectors in the same direction. 2mv sin theta, there you go in that direction. 2mv sin theta in that direction. So this is how you find the momentum change acting perpendicular to momentum change acting perpendicular to the bottom surface. Perpendicular to the bottom surface. 2mv sin theta. 2mv sin theta. Right. Part B. Follow the question order carefully. Yeah? Part B. Sorry, Roman 1, Roman 2. Roman 1, Roman 2. Very good. If the number of air molecules hitting the wing during 1 second is n, number of air molecules colliding per second is n. Using the result in A Roman 1, obtain an expression for the vertical force generated by the collision of air molecules which in terms of mv, theta and n. Vertical force. Careful. Let's find the force in that direction, then you can take the component. Right. So these on air molecules. Force on air. Force on air molecules. Force on air molecules is momentum change divided by time. Momentum change divided by time. Momentum change is 2mv sin theta in that direction divided by time is per second. Number of molecules per second means 1 over t is n. 2mv sin theta. Because not only one mass, now n number of masses, n times n per second. 2mvn. Remember in that direction, this is force on air. Force on air. Every action has equal opposite reaction. Force on the air molecules in that direction. Force on the wing will be in the opposite direction. Look at this. Force on the air molecules will be in that direction. Force on the wing will be in the opposite direction. You can write here. Force on a wing. Newton's third law. Every action equal opposite reaction. 2mvn sin theta will be in the opposite direction perpendicular to the surface. If I mark it here, I'm going to mark it here. Force in that direction is 2mvn sin theta. That is not what they are asking you. They are asking you to find the vertical lift. Don't be in a hurry. Vertical lift. Horizontal, vertical 90. This is 90 minus theta. Therefore, theta here. Don't forget. If I find the vertical lift force, 2mvn sin theta cos theta in that direction. That's your vertical lift. So you can see this force on air molecules because you're finding the momentum change on air molecules is in that direction. Every action has equal opposite reaction. Every action has equal opposite reaction. Newton's third law. There will be equal opposite force. Here Newton's third law action is there. Once you have marked that force perpendicular to the wing, you have marked that force perpendicular to the wing, then what? Now from there you have to find the vertical lift. There's a force first, there's a force sin acting in the opposite direction. Okay, right. They're asking you to find the vertical lift force generated. So here in this picture itself, I can show the vertical lift force generated. Vertical lift force generated is 2mvn sin theta. 2mvn sin theta plus theta. So vertical lift force generated. Vertical lift force generated on a wing. On a wing that is equal to 2mvn sin theta. 2mvn sine theta cos theta. Once you need it, carefully write it down. Carefully write it down. Okay, no? Right, perfect. Right, part B. Part B. When the airplane is moving, a wing sweeps the effective cross-sectional area A, and therefore molecules in a volume AV hit the wing during 1 second. Let the density of air be D, the volume flow rate AB times C. Write down the total mass of air molecules hitting the wing in 1 second in terms of AVD. So AVD is actually mass flow rate. So mass of air hitting the wing. Area of one wing. V volume velocity into density D, AVD. Hence, express N in terms of NVD. Yeah. Mass of air hitting the wing per second. So here, the expression is this: mass of one molecule is N. N number of molecules are hitting per second. Mass of one molecule is N. N number of molecules are hitting the wing per second. Yes. And this is given by the relationship. This is given by the relationship AVD. One mass, one molecule mass is M. N number of molecules are there. So M times N per second. So total mass per second Mn. Here per second. Here kilogram. Here also kilograms per second. So now this you can say N is equal to AVD over simple M. AVD over simple M. Okay, no? So mass multiplied by number of molecules per second. So mass flow rate. Mass flow rate is also AVD. From this, you can check the unit. Number of molecules per second into kilogram, kg per second. Here also kg per second. From there, N you can find. Roman 3. Obtain expression for the total vertical force generated due to collisions of air molecules on both wings in terms of AVD and T. The total vertical force, now this only did for one, na? Total vertical force 2mvn sine theta cos theta. 2mvn sine theta cos theta for one wing multiplied by 2. This is number of wings. The aeroplane, there are two wings. I don't know. I have not seen aeroplanes with one wing. Two wings are there. So multiply by 2. That's like common sense. Now, what are they asking you? They're asking you to write the relationship here. No N. Instead of N, we have to substitute this. AVD over simple F. 2 sin theta over cos theta. Am I having theta here? Yes, theta is there. So now what I'm going to do? M and M will cancel off. The total vertical force. Total vertical force due to collision. Here you will have 4 times A V squared D. A V squared D sin theta cos theta. Sin theta cos theta. Because two wings are there, you have to multiply this by 2, guaranteed. 4 times A D V squared. A D V squared. Sin theta over cos theta. There you go. Correct? No? There you go. The total force due to collision. Total force due to collision. Right. Total force due to collision is taking place. Roman number 4. If theta is 10, A is 25, D is 1.2, obtain a value for F in terms of V. Okay. Super. Now I'll do a substitution. 4 times area is going to be 25. V squared density is 1.2. Sin 10 cos 10. That's 10 degrees. 100, 1.2. 120 V squared. Sin 10 how much? Sin 10 is 0.2. Cos 10 is how much? 1. Simplify it, 24 V squared. That is the total force due to collision. Total vertical force due to collision. Don't forget that. Total vertical force due to collision. What have we just found? We are just focusing on how air particles are colliding and rebounding and creating what? A force on the wing. So air particles collide and rebound, There's a force on air particles, equal opposite force on the wing. Equal opposite force on the wing can be found. Take the vertical component is found. From there now we have simplified it and found the total force due to collision acting on the wing. Total force due to collision acting on the wing. Right. Part B, that's a very important, interesting part. Right. Then we have part C. Part C, Roman number 1. Assume that because the shape of the wing, the average speed of air streams relative to the plane just above and just below the wings are 7V over 6 and 5V over 6 respectively. Take P1 to be the pressure just above the wing, P2 to be the pressure just below the wing. So the pressure difference across the wing due to the Bernoulli effect is given by this relationship. Right. Here you go. As usual, here above the wing it's going to get closer, below the wing it's going to keep going. According to our theories, we know pressure here above is P1, velocity is 7V over 6. Pressure below is P2, velocity is 5V over 6. 5V over 6. Right. I can't apply Bernoulli here and here along a single streamline. I must appear. It can't be in two different places. So somewhere far away we have the same pressure with the same velocity 5V over 6. Along a single streamline I must apply. Height difference is negligible. Height difference is negligible. Apply Bernoulli P1 plus half density D. Half density of air. Velocity 7V over 6 square. 7V over 6 square. Height difference is negligible. Pressure P2 plus half D 5V over 6 square. Larger the velocity, lower the pressure, lower the velocity, higher the pressure. So from here we can say P2 minus P1 is half D 49 V squared over 36 minus 25 V squared over 36. Simplify this. P2 minus P1. Density is given, I think earlier it's given 1.2. 36. 49 over 25 is 4. 2. Simplify. T2 minus T1. 2, 12. 6 times 4, 6 times 6. 2 times 2, 2 times 3. Here 0.4 times 3. 2 times 1, 2 cancel out. 0.4 V square. T2 minus T1, 0.4 is going to be 4 over 10. That's 2 over 5. Pressure difference can be found. Pressure difference can be found, no issue. If the effective surface area of one wing is 120 meters squared, don't confuse. Earlier is swept area. Here is now effective area. Find the total vertical force on both wings, say FB, due to the above pressure difference. Be careful. Don't be in a hurry. Vertical or perpendicular effective area is there. For the effective area, there will be a force. Pressure difference into 2 aeroplane wings, 2 times weight. We now want the vertical component. We now want the vertical component. If you now want the vertical component, remember here theta 90, 90 minus theta, here theta. Vertical component here. Vertical component 2 times T2 minus T1 times A cos theta. That is the vertical total Bernoulli force. Simplify the relationship carefully. Roman 2. Total vertical force on both wings due to Bernoulli. Due to Bernoulli. 2 times T2 minus T1 times area. That is going to be cos theta. That's it. 2 times T2 minus T1 is 205 V square. Area is 120. Cos 10 is going to be 1. 5 times 1, 5 times 24. No? 5 times 24, 24 times 4. 24 times 4. How much? 96 V squared. That is due to Bernoulli. Forces due to Bernoulli. Total vertical force due to Bernoulli. There you go, can be found. 96 V squared. Now remember, the wing is having a vertical force due to Bernoulli and a vertical force due to collision. Okay. Very good question. Top level question. Okay. That is C Roman 1 and C Roman 2. So total vertical force acting on both wings due to Bernoulli is 96 V square. 96 V square. Right. Now what? Part B. Part B. If the mass of the airplane is 4.32 10 to the power 4, calculate the minimum speed required for the plane to take off. Minimum speed required for the plane to take off. Here you go. Draw all the vertical forces separately now. Vertical force due to Bernoulli, 96 V square. Vertical force due to collision, 24 V square. Vertical weight, 4.32, 10 to the power 4 times G. So just to take off, they're asking vertical. No? Minimum speed at takeoff. On the verge of moving up. On the verge of moving. Upward vertical forces balances downward vertical force. Vertical forces are balanced. 96 V squared plus 24 V squared. that is equal to 4.32 10 to the power 5 Newton. Simplify it, 120 V square, 4.32 10 to the power 5. V squared is equal to 4.32 10 to the power 5 divided by 120. V is equal to square root 4.32 10 to the power 5, 120 square root. From there you can get the answer. From there you can get the relationship. It's just perfectly simple work. Perfectly simple work. Huh? To get the relationship, 60 meters per second. To calculate this, 60 meters per second. 60 meters per second. Part E. If the maximum possible acceleration of the airplane on the runway is 0.9, assume that the airplane accelerates uniformly, calculate the minimum length of the runway, must have a takeoff. E squared equal U squared plus 2AS. Final takeoff velocity is 60 squared starting from rest. Acceleration 0.9 was the runway distance. 3600 divided by 1.8 is S. S is 36,000 divided by 18. 2000 meter runway is needed. 2 kilometer runway is needed. Here, takeoff is going to be 60.9 ms minus 2. So the runway is going to be 2000 meters or 2 kilometers. Right. Got it. Pilots take off airplanes by accelerating against the direction of the wind whenever possible. Explain the reason. If you take Katnayaka International Airport also, technically early morning, wind will travel from the sea towards the land. All the planes take off towards the Katnayaka Lagoon. Because what happens when you are going against the wind, the air molecules colliding with the wing also will help actually. Air molecules colliding with the wing also will what? If more air molecules are, if the plane is going in that direction, more air molecules colliding, there's an additional help no by this vertical force. So the plane can take off in a shorter runway. Yeah. Plane can take off in a shorter runway. Right? Right there. When the plane takes off against the wing, force due to collision of air particles will be higher. Force due to collision of air particles will be higher. Therefore, the plane can take off in a shorter runway. Therefore, the plane can take off in a shorter runway. Therefore, the plane can take off in a shorter runway. Right. Okay. So I hope very good question. Look at it back again. From this, you can see the level that you should work, the level that you should understand the theory, and how you should apply it very freely. When they say vertical, some letters are put in bold letters. You should look at those words carefully. Then you have no problem at all. I hope you enjoyed the session. As always, I'll catch you same time next week. Till then, keep working, be positive, always focus on your growth, your personal growth, and that will never fail you. Okay. See you next.